The next thing to talk about is what's called the Chinese remainder theorem. So this is the Chinese remainder theorem. So the story I was told of why this is called the Chinese remainder theorem is that back in ancient China, they would give each other kind of these mathematical challenges, and they would be something like this. So they would say, find a number that's congruent to 3 mod 10 and a number that's congruent to, say, 4 mod 7. Okay, and so here's a system of equations. Find a number that's congruent to 3 mod 10 and congruent to 4 mod 7 at the same time. This is apparently how Chinese nobility used to challenge each other mathematically. So they would lay out these challenges, and of course they used to be worded slightly differently. They wouldn't use this notation, but they would say, "I'm thinking of a number so that when you divide it by 10, you have a remainder of 3, and when you divide it by 7, you have a remainder of 4. Find that number." Okay? Or find a number like that. Of course, there's infinitely many. It turns out that this will have a unique solution. This has a solution mod 70. Okay, so this, in our case, we'll have a unique solution mod 70. And in general, we're going to have a unique solution mod. So if we were to have two moduli here, we would have a unique solution mod, say this is mod m and this is mod n. We'd have a unique solution mod m times n whenever they're relatively prime. So here it's important that 7 and 10 don't share any common factors other than 1. So they're relatively prime. If you have two numbers that are relatively prime, then you might not be able to find a solution, or you might be able to find more than one solution. But we're going to concentrate on when those two moduli are relatively prime. And I don't really have too much of a way here. We could go through and we could talk about a systematic way to solve these. And I do have that right up in our lecture notes if you want to go through and figure out how could you actually systematically solve these systems of equations. But I want to just mention that this is a theorem, and then I want to kind of move on. And so really I don't want to linger too much here. What I will do is let's think about how to solve this system, and then you can try and solve some other systems from the notes if you'd like. So this has a solution mod 70. So what I'm going to do is I'm going to think about what are the numbers that are congruent to 3 mod 7, or actually what are the numbers that are congruent to 3 mod 10 or 4 mod 7. I'm going to start with 4 mod 7, and I'll explain why in a second. But if x is congruent to 4 mod 7, that means that x is, let's see, it could be 4, could be 11, could be 18, could be 25, 32, 39. Just keep adding 7. So these are all multiples of 7 plus 4. Of course, we could also have -3, -10, and so on. But since we know that there's going to be a unique solution mod 70, I just need to go up to 69 here. So from 0 to 69, because that's all the remainders that you can get when you divide by 70. And so we would have, let's see, if we keep adding 7s, we're going to have 32, 39, 46, 53, and we can stop because 53 is a multiple of 10 plus 3. So that's going to be 3 mod 10, and it turns out that that's our solution. So what I like to do is I like to take one of these congruences. In our case, I picked x is congruent to 4 mod 7. Think about all the multiples of 7 plus 4 that you can have from 0 to 69 in this case. And then find the ones that are congruent to 3 mod 10. Now you could have also done this game with thinking about starting with x is congruent to 3 mod 10. These numbers are easier to find, right? You get the axis 3, 13, 23, 33, 43, 53, 63. But the problem is that now you have to go through and think about what are all these remainders mod 7. I think it's actually easier to start with the multiples of 7 plus 4 and then find the ones that are congruent to 3 mod 10, because being congruent to 3 mod 10 just means that your ones digit, your final digit, is a 3. Okay, so I think that that's easier to find, so that's why I started with the other one. So let's do one more and then we'll move on. So one more. Let's say I want to solve x is congruent to 5 mod 8 and x is congruent to 3 mod 9. Here, whatever you want to do is fine. If you want to start with one over the other, it's not a big deal. Let's start with 5 mod 8, I guess. So if x is congruent to 5 mod 8, so if x is congruent to 5 mod 8, that implies that x is, let's see, 5, 13, 21, 29, 37, 46. By the way, 8 times 9 is 72, so we're going to go from 0 to 71 in this case. And we're just adding 8 each time. Something seems amiss here. Can I add 37? No, I can't add. It's not 46. 45. It's embarrassing to be live on YouTube here, but here we are, 53, 61, 69. Those are all the integers that are congruent to 5 mod 8 from 0 to 71. Now, which of them are congruent to 3 mod 9? Let's go through and let's look. So we want them to have a remainder of 3 when divided by 9. So certainly not 5. 13 is 4 mod 9. 21 is 3 mod 9. And then this is 2 mod 9, 1 mod 9, 0 mod 9, 8, 7, 6 mod 9. So it turns out that 21 is our solution, and there we go. So it turns out our solution to the system. So our solution is that x is congruent to 21 mod 72. And we have a unique solution mod 72 because 8 and 9 are relatively prime. When 8 and 9, when the moduli are not relatively prime, you lose that uniqueness. Okay, and so I'll leave it to you to figure out what happens in that case. Again, I have a little bit of this written up in our lecture notes. We can talk about it sometime during class if we like, but this is the basic story. So again, this is the Chinese remainder theorem.